Hi, my name is Shahnawaz. In last lecture, we did some operations on modules. Um, Now, in this lecture, we are going to do first some short exercises on these operations. So we have an exercise. So let us consider modules, say M and P. So let M, N, and P be A modules. Then we have annihilator of the sum of these modules. So this sum is actually a module which contain the elements of the form say sigma mi plus ni, where this I runs from 1 to n, where n is some natural number, i.e. this m plus n is actually a finite sum of elements of m and n. So we have to prove the annihilator of this module is actually the intersection of annihilator of m and annihilator of n. So this is our first exercise, and the second one is annihilator of n colon p. Note that the colon of these two modules is actually an ideal of A. So this, if this n and p are A modules, then we define their colon to be the set of elements of A such that A times p is a subset of n. Note that this is an ideal. So the annihilator of this thing is actually the annihilator of the quotient n plus p mod n. Let us prove the first one. So let us first consider x to be an element of this intersection. So let x be an element of this intersection. So that means this x will annihilate both m and n. Or this will imply x will annihilate their sum as well, because this m plus n is actually the set of all finite sums on their union, since the module m plus n is the set of all finite sums on m union n. So hence, so if this x annihilates this thing, sorry, this is 0 here, so hence x is in the annihilator of the sum of these modules. So conversely, let x be an element of the the sum of the annihilator of the sum of these modules. So then, now note that m and n are both subsets of m plus n. So then xm will be 0 and xn is also 0. The reason being this m and n are subsets of m, since m and n are subsets of m plus n, that is now this x inherits both m and n, so this means this x is an element of the intersection of these two annihilators. So this shows the annihilator of sum is actually the intersection of their annihilators. Now let us prove the second one. So now we are going to prove the annihilator of this column is actually the annihilator of this quotient here. So let us first suppose, so let x be an element of n colon p. I mean, this is not annihilator here, this is actually just column here. So let us consider this x to be an element of this column. Then by definition x times p is contained in n. So we have to prove this x annihilates this quotient here. So it suffices to prove x annihilates any arbitrary element here. So let us pick n. So let z be any element in the quotient of these modules. So to prove this x is in the annihilator of this module here, it suffices to prove this x annihilates this z, because this z was chosen arbitrarily. So now z being an element of this module, it has the form, so then z has the form, so this z is going to be equal to sum of items from 1 to n, ni plus sum of these little pi's, where iron is from 1 to m plus n, where n, let us say this is j here, where this ni and pj, I mean ni is element of n and pj is element of p for all I and j. Now let us check whether this x annihilates this element here or not. So now xz, that will be the element x times the element here I goes from 1 to n, ni plus j goes from 1 to m, pj plus n. So that is going to be equal to sigma I goes from 1 to n xni plus sigma j goes from 1 to n xpj plus xn. Now note that ni is being element of n, so xni be an element of n. Hence this is going to be an element of n, i.e. this n absorbs this element here. And now similarly this xp being a subset of n implies this is also an element of n, because this element here, this is an element of xp, and xp is contained in n. So this is actually equal to n, which is the 0 element in this set, in this module here, which is actually the element 0 bar. So hence x is in the annihilator of this quotient module. Now conversely, let x be an element of this quotient module, then this x annihilates this module, i.e. then x times n plus p mod n is actually the 0 element of this module, which is n. Or this x is going to annihilate each element of this module. Now an element in this module looks like, so this is going to be n plus p plus n is actually n. On simplifying this, we get so this is actually true for all n in n and p in p. So this would imply, so that means this x times n plus p is actually an element of n by using the properties of cosets. So that is, i.e. xp is in n for all p in p, or xp is contained in n, hence x is an element of n colon p. Now in previous lectures we proved that if suppose we have an a module m, so this m is what a module which is cyclic, i.e. which is generated by some element x. So this m is cyclic if and only if this m is actually isomorphic to some quotient of r, where I is some ideal of r. Now we'll try to generalize this statement. So I mean, what would happen if this m is finitely generated? So let us call this a proposition. So let m be an a module so this is our a module. Then we claim this m is finitely generated, then m is finitely generated if and only if m is isomorphic to some quotient of a to the power n, where n is some natural number. So let us prove this. So the proof is straightforward. So let m be a finitely generated a module, and let this m is generated by the elements say m1 through m n. Now we can define define a map phi from a to the n to m by phi takes the element a1 through an to a1 m1 plus so on an mn. Now this m being a finitely generated module generated by these elements, each element in m is of this form over here. I mean, this is an element of m, so this map is actually well defined. So if we if this m is a vector space over a, where a is some field, then this n tuple over here, this is called the coordinate vector of this element in the vector space. So if this is over vector v, then this element in the field is called the coordinate vector. So it is the analogous version of that result in linear algebra. So clearly this is this can be easily verified that phi is a linear map. I mean, it is a module homomorphism. So clearly phi is an a module homomorphism. So one should verify this. So not only that, this phi is an a module homomorphism onto m. I mean, this phi is surjective because each element in m is going to look like this, because this m is generated by these elements. So now invoking the first isomorphism theorem, so then by first isomorphism theorem, on modules a to the power n mod, it is kernel, I mean the kernel of phi, that is actually isomorphic to m. So this proves one direction. So conversely, let a to the power n mod kernel of phi is isomorphic to m. Now we have to prove this m is finitely generated. So if this is the case, this means then we have a module homomorphism, say phi from a to the power n onto m. This follows from this. So now this an being the finitely generated, i.e. It has the generators e1, e2 through en, where ei is some n tuple, say 0 0 so on 1 0 0 0, where this 1 is at the ith place. So this is in some sense a standard basis of a to the power n. So if ei is 0 so on 0 1 0 so on 0, this 1 being at the ith place, so let us write this down, the 1 being at ith place, then these EIs, so then E1 through En generators a to the n, and so this generators a to the n. So if this is the case, hence phi of EI generators m. So then phi of EI, where 1 is lesser equal to I is lesser equal to n, this generators m, that is if phi of EI is this little mi, then this m is actually generated by m1 through mn. So this proves this result. Now let us prove this is an important result. So this is a proposition. So let m be a finitely generated a module and let I be an ideal in A. So if phi from m to m is an A model homomorphism, I mean this phi is an A endomorphism, such that the image of m is contained in Im, then this phi satisfies an equation of the form phi to the power n plus a1 p to the power n minus 1 plus so on plus a n minus 1 phi plus a n, which is 0. Actually this is p to the power 0 here, which is the identity map, where these AIs, this is in the ideal I. Actually these AIs are in the power of ith power of I. So I will tell you what this means at the end of the proof. So let us prove this. So m is given to be a finitely generated A module. So let us choose a basis for m. So let m1 through mn be a set of generators of m. Now this phi is actually an element of home mm. Now home mm being the set of endomorphism, so we sometimes denote this set by this set of endomorphisms of m. Now this phi being a morphism from m to m, I mean the module homomorphism from m to m, with the condition that this phi of m is contained in the Im. So we will define this phi. We have to define this phi such that this is true. So now phi of mi being an element of Im. Now to define this homomorphism, it is enough to write the images of these generators, because if we know the images of these generators, we can have the image of whole M. So we are going to define this phi only on these little mi's. I mean so we have phi of this little mi. This is the element j I goes from j, runs from 1 to n, a I j mj, where this I runs from 1 to through n. I mean we are defining the images of the generators. Now note that so these aij's, they are the elements of I, and this mj is a generator. So where this aij is in I, so one can note that this is an element of Im. So this phi makes sense. Now for different values of I, these are I mean for I runs from 1 through n, these are the n equations. So we can write these n equations in the matrix form as, so we can write the above system of equations in matrix form as, so this is like this. So we have phi of m1 here. Similarly we have phi of mn here, because we have n generators. So this is going to be equal to a11 a12 through a1n, then a21 a22 through a2n. Similarly this is an1 an2 through ann, and we had this vector here m1 say m2 through mn. So this would imply or, so let us take the RHS to the left hand side. We get a matrix like this. So this is phi of m1, so this is minus a11. Actually this is n cross 1 matrix here, this is n cross n, and this is n cross 1 matrix. Then we have minus a12, so on, minus a1n. Then we have a21, then phi of m2 minus a22, so on, minus, this is minus here, a to n so on. This is minus a n 1 a n 2. Let us write this term here. This is minus a n 2 so on minus a n phi, I mean this is phi of mn minus a n n times this vector here. So this is actually 0 here. Now each entry in this matrix, so each entry in this matrix is an element of a phi. Now by a phi we mean the set I goes from 0 to say n ai phi to the power I, where these ai's are the elements of a and n is a natural number. So note that this a phi is a commutative subring of the endomorphism ring of M. So let us first write this down here. So if I look at the set home MM, i.e. the set of all A module homomorphism, which is sometimes denoted like this. So this is actually a ring, but this is not I mean this set over here, this is a ring, and the multiplication here is the composition, and this has also but this ring over here is non-commutative, because if I take two endomorphisms f and g, then f dot g is not equal to g dot f. Now each element in A, so if A is an element in A, then this A can be identified as an endomorphism of M. I mean each A and A can be identified as a module homomorphism from M to M, which takes an element x here to the element A times x. I mean each element in A can be identified as a module homomorphism, which is in this case the multiplication map. So this A is contained in some sense in this ring, endomorphism of M. Now so if each element of A is an endomorphism, then so is this ring, I mean the ring A adjoined with this phi, which contains the elements of the form ai phi to the power I, where I runs from 1 to n. This ai is in A, and this n is a natural number. Now note that each constant in A, this can be identified as an endomorphism of M, and phi is given to be an endomorphism because phi is a map from M to M. So is any power of phi. So that means this A to the power A adjoined with phi, this is actually a subring of the endomorphism ring of M. Now note that this ring is non-commutative, but this ring over here, this is the commutative ring here, because this is same as x times A, and this phi to the power 2 is same as phi with phi, which is same as phi with phi. So each entry in the n cross n matrix above is an element of a phi, which is the set ai phi to the power I, where I runs from 0 to n. ai is an a and n is a natural number. Now note that a phi is a commutative subring of the endomorphism ring of M. Therefore, the n cross n matrix, I mean this matrix over here, therefore the n cross n matrix is an element of the set of all n cross n matrices with entries from this commutative ring. So we know in linear algebra, if we have a matrix A in this I mean the n cross n matrices with entries from a field F, then we know A multiplied with the adjoint of A is actually the determinant of A times I, where is I is an n cross n matrix, identity matrix. But for this the entries must belong to the field. I mean this is also true if we replace this M with a commutative ring with unity. So this works as well, because this, so I mean for our matrix which is in the matrix ring Mn with entries from the commutative ring A phi, so for this matrix this identity is true as well. So by multiplying on, so by multiplying, so let us call this star here. So by multiplying star on both sides by the adjoint of A, I mean by the adjoint of the n cross n matrix, by this n cross n matrix I mean this matrix over here. So we have, so we get the determinant times this matrix, so we get, now this is the determinant, we get determinant of phi of M1 minus A11 minus A12 through A1n, then A21 P of M2 minus A22, so on A2n, and then A minus A, this is minus minus, minus AN1 AN2, so on phi of Mn minus ANN times the identity matrix In and this column vector m1 through mn. So this is actually equal to 0. So on expanding this determinant, this determinant, which is actually a function, so this is this determinant is actually an element of a phi. So note that the above determinant is an element of a phi because the elements in this matrix were the elements of a phi, so is the determinant of this matrix. Now this is this determinant is actually the endomorphism of M. So but this endomorphism is such that it annihilates this vector. Now this vector being this element here is the arbitrary element, so it will annihilate each element in M. So hence this determinant is the zero endomorphism of M. So expanding this determinant, we have an equation of the form expanding this determinant, we have an expression of the form phi to the power n plus a1 phi to the power n minus 1 plus so on plus n is actually 0. So this proves what result. So let us see what would happen if this matrix is a 2 cross 2 matrix. So let us expand the determinant. So if we look at this determinant, so it is phi of m1 minus a11, then minus a12 minus a21, and phi of m2 minus a22. So this is actually phi of m1 minus a11 times phi of m2 minus a22 minus a21 a22. Now if we look at this determinant and we take this m outside, so we have an expression of the form, so we get let us forget these mi, so we get phi squared minus a11 plus a22 phi, then we have plus a11 a22 minus a21 a22. So note that this coefficient is so if we look at so this is actually phi square minus let us take minus inside, and this is a1 times phi plus a2. Now this a1 is element of this form, which is the sum of two elements of I. So this element is in I. In particular, this element is in a to the power 1, and this element is again an element of I, but this is sum of elements of product, I mean sum of product of two elements of I. So this element is actually an element of I to the power 2. So likewise, if I take this matrix to be of order 3 cross 3, then AI will be an element of I to the power I. In particular, I to the power I is a subset of I. So this proves this determinant trick.